Probably all of you have heard of or even work with interacting particles. So they could be charged particles or positive or negative charges that attract or repel each other with a Coulomb interaction. Or it could be gravitational force that attracts the Earth to the Sun or any of you to the Earth. However, photons that are the basic quanta or the basic particles that compose light are massless and neutral. So they have zero mass and zero charge, and therefore they don't interact with each other. So if any of you dreams about having this cool lightsaber fight, it's actually impossible in real life, because when you shine two light sources on top of each other, photons simply pass through and nothing happens. So you actually can make photons interact. You just need some mediator, and no, it's not Pakistan, it's some optical it's some optical medium, so it could be a crystal or some gas. But there's a catch, so these interactions are usually very, very weak and inefficient. So you need to send very intense light fields, many photons, but only few of them will actually interact. So we want to ask, how can you make light interact with itself at a single photon level? So we want to send only 2 photons and be certain that they will interact. And our motivation is that we want to build a photonic quantum computer. And if we want to do it efficiently, we need to have these photon-photon interactions. So the answer to the question is that we need strong interactions, and we're going to achieve them using something called Rydberg blockade. So once again, it's not the one in the Gulf. We use Rydberg atoms, which are atoms that are excited to very high orbitals. And it makes them very big, so a single atom can get to the size of 1 micrometer, which is the size of some bacteria. And these atoms interact very strongly with each other with interaction called the van der Waals interaction. And this interaction is also very strong, which allows us to define a radius called the Rydberg blockade radius around each atom. So there's actually a sphere the size of this radius where only a single Rydberg atom can exist. And this radius is even larger, so in our case it's 12 micrometers, which is larger than blood cells. So imagine a sphere larger than a blood cell where only 1 atom can exist. So how do we use that to make photons interact? We need to find a way to take a photon, connect it to the Rydberg atom, so that when we have another atom connected to another photon, we can translate the Rydberg atom interaction into an effective photon-photon interaction. So we're only missing this link, and this link is called Rydberg polariton. So Rydberg polaritons are simply a hybridization of a photon and a Rydberg atom, and they inherit the van der Waals interaction from the atoms. So how does it look? We have a cloud of atoms, which is elongated, and we send a photon into the cloud. So now when the photon enters the cloud, it becomes this polariton, and it starts propagating in the cloud with the Rydberg blockade radius around it. So now it propagates until it reaches the other side, and then it leaves back as a photon. Now how does the interaction look like? If we send 2 photons with some distance or large delay between them, each one will enter the cloud, reaches the other side, and leaves. However, if we send 2 photons with a small distance or small delay between them, when they enter the cloud, they will be inside the blockade region of the other. And as we said, inside this sphere, only 1 Rydberg atom can exist. So when they meet inside the cloud, only one can survive, while the other one will be absorbed. So now if we look at our system, we can say that photon pairs are suppressed, meaning that photons can't come out of the medium together. And we can say that we can only get single photons out of the medium, so photons can come out one by one. Now we call this system the co-propagating geometry because both photons go in the same direction, so they kind of chase one another. And what we're interested in general is something called the interaction range. So we want to ask what is the largest delay between the photons that will allow them to interact. And it turns out that in this system, the interaction range, which is some time scale, so we mark it as t, scales like a square root of the optical depth, OD, which is simply the cloud size. And it has some very easy intuition. So if you make the cloud longer, the photons have more chance to catch up and meet and interact. So if you increase the cloud size, the interaction range will increase. Now, in general, we want this interaction range to be as long as possible. And if you want to increase it, the simplest way is simply make the cloud longer. But we can't have an infinitely long cloud, so we can only increase it up to some point. And if we really want to increase the interaction range further, we need to find some other way. So we want to change the way the interaction range depends on the cloud size. We want to beat this scaling, we want to have some different expression. And back to our motivation, if we want to build a quantum computer, we need to have this interaction between photon pulses. But in this system, because of this dependence of the square root, there's a fundamental limitation that prevents us from using pulses. So this system is useless for quantum computing. Okay, so now it calls for some more dramatic change. And what we do is we send the photons from two opposite sides. So now instead of chasing one another, they go towards each other. And now the interaction range increases. And there's also a very simple intuition for that, because now when the photons go towards each other, we know that they must meet at some point. So only condition is that they need to meet inside the cloud. So now the interaction range scales linearly with the size of the cloud, which is larger. So let's see how we measure that. So we have our system, and we send a constant weak flux of photons into the cloud. So we have some random probability to send photons into the system, and we don't know when, but we just measure what comes out. And now, after the photons enter the cloud, we measure them from the other side using single photon detectors. So whenever a photon reaches the detector, we get a click. Now, after we measure that, we can count the number of coincident pairs that we got, meaning pairs of photons that arrived either at the same time or with some delay. So they could be exactly the same time or one after another, but we just count that. And now we are ready to calculate our final result, which is our holy grail, which is called the two-photon correlation, G2. So it's basically the ratio between the number of pairs that we've got and the number of single photons. Now, it's, in other words, just the ratio between how many pairs of photons we measured and how many pairs of photons we expected to measure. So now, for any typical light source, the sun or even a laser pointer, this ratio will be greater or equal to 1, meaning we either get exactly the number of photons that we expected or maybe even more. So in general, for any classical light source, any typical light source, photons tend to arrive together. The interesting thing happens when this value goes below 1. So when it's below 1, it means that we get less photon pairs than expected, or in other words, we are measuring single photons. So our photons arrive one by one. And this is a signature of quantum light. So if we think about it, this is exactly what we expect to measure in our system. Because as we said, photon pairs are suppressed, and photons can only leave the medium one by one individually. So let's see how we measure that in our system. So what we're going to see here on the y-axis is this ratio, and on the x-axis, it's the delay between the two photons. So when the delay is 0 in the center of the graph, the photons arrived exactly at the same time, but towards the edge of the plot, the photons arrived with some delay. And now we start with the previous geometry, the co-propagating one. So now the photons propagate together. And what we measure is this. So let me walk you through this. So first of all, we see that we have a dip that goes below 1. So as we expected, we are indeed measuring single photons. But we can also look at the width of this dip, and this will be exactly the interaction range that we talked about. So in this case, we see it's 1 microsecond, meaning that photons that arrive within 1 microsecond of another will interact. Now let's see what happens in our new geometry. So now we get this plot. So we can immediately see that the interaction range increased, the width is much higher, and it's actually more than twice as long as the original one. And so we are able with that to confirm that the interaction range increased with our new system, And I won't have time to show you that, but we can also measure this as a function of the size of the cloud and confirm this new scaling. And we are also able, with that, to show interaction between full pulses as a step for quantum computing, and that's something that we weren't able to do before. So with that, I will finish, and I want to thank the rest of my lab and the rest of the group and everyone who is here and listening.